All right, everyone. I'm going over chapter 12 and 13 today, so you can take a look at it. I do want to show you something on our Canvas. If you go to announcements, there is a copy of the practice final exam. I also have them here in person. I'm going over this at 9:30. It will be recorded. This is tomorrow because I messaged it last night. It will be recorded. I'm going to post it on Zoom. Tonight. When I get home, I'll have it up tonight by like 6. I recommend like getting all your homework done first, and then like I'm gonna do like a little 15-minute clip where I like show people like give the instructions clearly, because the instructions to me are pretty clear, but I always get students that don't know what the fuck they're doing on the final. It's terrible. So I'll give you like the instructions and then like how I would tackle it. And then I'll pause it, I'll put a little gap in the video and then do the answer, like walk through the answers. If you're at home, I recommend like not watching how to do the answers first, doing it on your own, and then comparing what I got with what you got. I'm also going to scan it so you don't need to like watch the video for the answers. But it's available to practice. This is very similar, almost. I'm not going to say almost identical because the word problems are different, but there are 10 problems. It's the same categories. I'm not pulling any punches. All right, so let's take a look at chapter 12 and 13. There's only 3 sections in this stuff.
So there's only going to be like 10 questions on the final exam?
That's correct.
Nice.
2 of them are confidence intervals. 1 is for mean, 1 is for proportions. In chapter 10, you learned 2 hypothesis tests. In chapter 11, we did 3 hypothesis tests. That's 5. We're doing 3 more for a total of 8, and there's 8 more questions. Guess how many? Guess what you're getting on those last 8 questions? 1 hypothesis test from each section. Chapters 10 through 13, one question per section. All right, so we're doing chapter 12 and 13. These are hypothesis tests for 3 or more samples / groups. So chapter 11 was on 2 groups, chapter 10 was on 1 sample or 1 group. 12.1 is on the goodness of fit test. This test is how well does the data match what we expect? This is a section that you would have to normally, or you're going to probably have to use a calculator for. If they don't give you the expected value, you have to calculate it. If they don't give it to you, they'll give you a percentage. The expected value for any individual group is n times p. P, I'll put I for the ith group. There are 2 rules. All expected values must be greater than 1 or equal to 1. And 2, no more than 20% of the groups is less than 5. I'm sure they're going to ask you a question like this on the homework. So there's another way to rephrase this last one. You could also say at least 80% of the groups are greater than 5. That's the other way of looking at it. We'll throw the equal sign in there, not just greater than, but greater than or equal. So we still are, in this section, we're still doing our 5 steps for the hypothesis test. You still got to do all 5 steps. We've been talking about the last 2 days, how, or at least yesterday, the 5 steps. The first step is the only step that changes. The first step has H naught and HA. So let's talk about what H naught and HA is for goodness of fit. H naught is observed values match expected values. And HA is at least one group doesn't. And how we find this in StatCrunch is stats goodness of fit. And unfortunately, it's called, the next thing is chi-square test, which sucks because the next test is actually called the chi-square test for independence. So it looks similar. Chi, that's the symbol chi. So chi-square is like that. It's like pronounced like chi, like bi. You're saying like bi, but you're using the K sound instead of the B. You'll need 2 columns of data. One column of observed data. And a column for expected unless they're equal percents. Which means all the proportions are the same. And I'll show you how to deal with that. So before we give an example, I do want to clarify something I said yesterday. It's the only time I've ever wrote it down wrong. I said everything right verbally, and I wrote some shit down wrong. So if you were here yesterday, or if you watched yesterday's video online, that one was good because it was from the next class and there's no mistake. If you were here in person yesterday I had said, step 4 for the hypothesis test. I said option A was, I'll show you, alpha less than p-value and then alpha greater than or equal to p-value. Notice I've got the words p-val's too low. It should be, I said alpha less than p. It should be p-values less than alpha. That's the difference. I just wrote them in the wrong order. So if p-value is less than alpha, p-value is too low. Reject the hoe. Support HA. And then B is if p-value is greater than or equal to alpha. If p-val is not too low, do not reject H naught. Do not support HA. And there is not enough evidence. The easiest way to remember these are the two jingles. Well, the jingle, if p-val is too low, reject the hoe. And then just go, okay, if that's not true, it's not. All the knots go together. It's not too low, we do not reject H naught, we do not support HA, and there's not enough evidence. All right, that was a little mistake I gave you guys yesterday. Let's take a look at, we're gonna look at question number 3 in the homework. Draw point 1, number 3. Did you guys need that up longer? I'm fucking over here racing through shit. I see. Okay. I figured out a way this morning, like 5 minutes before class, I figured out a way that I can just give full credit on fucking bad questions. So that's what, this week, tomorrow, I'm going through and I'm doing I'm checking for rounding on the midterm, and I'm going through all the fucking sections going, this question was fucking terrible, full credit. This question, there's a lot in the last few seconds. I have to, like, the next 2 weeks, I really need to change the entire system because I had the homework. It was awesome. And then they fucking updated the version, and I didn't know they fucking put all the shitty questions back in. They're bad questions. Okay, so this says a manufacturer of colored candies states that 13% of the candies in a bag should be brown. I'm gonna write this down because they're giving me percentages, and I'm gonna have to make some calculations here in a second. Brown is 13%, yellow is 14%, red is 13%, blue is 24%. Guess which candy this is? That they clearly didn't get fucking licensed to use the name of. Orange is 20%. And green is 16%. The only thing they're missing in this description is it just says colored candies rather than colored chocolate candies. This is the M&M distribution. M&Ms do not have an equal color distribution. Fun fact. In fact, M&Ms are produced in 2 cities in the entire United States. One's like in Pennsylvania or some shit like that, at like the Hershey place, and the other is like somewhere in the southern states, like South Carolina or something like that. But they produce different percentages, and I don't know why. It was a fun read when I looked this up. But this is the distribution they're saying. It says a student randomly selects a bag of colored candies. He counts the number of candies of each color and obtains the results shown in this table. So we're going to need to get the data from there. Test whether the bag of colored candies follows the distributed state above at the alpha equals 0.05 level of significance. That seems pretty important. I'm going to write that down, 0.05. The null hypothesis, H naught, is always that it matches what's expected. Expected in this case is going to be what the manufacturer says it should be. So we should have that H naught is the distribution of colors matches what the manufacturer says. And H1 is at least one of them is different, so it doesn't match. That looks like B says that. H0 is distribution of colors is the same as stated by the manufacturer. And H1 is that they are not the same. Now it gives us the frequency here. So I'm going to write this down on my table, and I'll switch over to the camera in a second. They had 61, 66, 56, 62. No, I hope they got them. Let me see. Brown, yellow, red, blue. Okay, in the same order. I already got them written down. Good. And 66. Is that what they have in this table? Yeah, and they got the proportions. That's not what we need, unfortunately. When we put this in StatCrunch, we actually need a value. So we're going to have to compute the expected count right here, right now. Expected count or expected value is what we should get if these percentages are correct. And it's equal to n times p. So first off, we need to figure out what n is. N is adding these numbers up. So I'm going to get out my calculator and we're going to do that. Already marking up my hands. 10 minutes, got ink all over my hands. $61 plus 66 plus 56 plus 62 plus 99 plus 66. This is a fucking big bag of candies you got. 410 fucking candies. That's a lot of candy. That's a lot of M&Ms, right? A normal bag of M&Ms is about 60 to 70 M&Ms. I know because this is a normal thing I do in stats classes when it's like not a 4-week blitz. I bring in M&Ms and distribute them. And we count them and we use them in one of these projects, in an experiment. I also normally have better attendance than 2 people showing up. What's the fuck point? That's not enough people to make a sample. All right, so let me double count that. I want to make sure I got the right number. So I'm going to do it again just to be sure that I get 410. I did get 410. Okay, so for here, I'm going to do 410 times 61 points times 0.13, the percentage. 410 times 0.13 is 53.3. Or 10 times 0.14 is 57.4. 410 times 0.13. We already did this on line 1. I don't need to recalculate it. It's going to be 53.3. 410 times 0.24 should be around 90 something, maybe 100. What? I did divide. That's the wrong button. 98.4. 410 times 0.24 is 98.4. So it looks like blue is like way low. Blue, we got 62, there should have been 98. I'm pretty sure that's going to say that we're going to have something that says this is off. 410 times 20%, that should be 102. Can't be. 24% was lower. Should be 82. Yeah. 82.0. And 410 times 0.16 equals 65.6. This is what they're asking for right now, the expected count. So we need to go in and put those values in. Okay. And then we will do our hypothesis test. I'm pretty sure it's coming up. 53.3, 7.4. Okay, now wants the test statistic. Oh, one way of doing this. Let's see if, nope, I can't even load that to StatCrunch. We're just gonna have to type these in. So maybe I'll type in the colors in to make sure I do the stuff correctly. And I will put observed here and expected here. Observed was 61, 66, 56, 62, 99, 66. And this is 53.3, 57.4. All right, before I do my thing, I'm gonna just double check all the numbers because I had to type them in manually. 61, 66, 56, 62, 99, 66 matches. 53.3, 57.4, 53.3, 98.4, 82, and 65.6. All right, we're good to go. We're gonna go stats, goodness of fit, chi-square test. Observed, I called observed. If all the percentages are the same, you don't need a column for them. You can click this cell that says all cells in equal proportion. But M&M decided to not make all their candies in equal proportion. So we have to tell it where the expected values are. That's it. The test statistic is the chi-square value, and p-value is what we're going to use for our hypothesis test. So I'm going to write these down. 19.529527, and p-value is 0.0015. Then I'm going to walk you through what you're going to see on the final for a question like this. To 3 decimal places, 19.530. To 3 decimal places here is 0.002. Okay, so now they got the end of the hypothesis test. Let's come over and do the hypothesis test the way you'll see it on your final. So you'll get the whole question on final equivalent. Will be like candy. It'll talk about the candies are distributed with these percentages. It will tell you that we got brown 61, yellow 66. I'm just writing down what the numbers we had here. Orange 99 and green 66. And I'll list the percentages by color as well. Then it will say something like this. The test statistic, we want to know if this follows the manufacturer's description. And then you'll see some shit like this. Oh, and I'll give you alpha on some of them. If I don't, this one gave alpha, so I'm going to give it. Then I'll say like test stat is, I'm not going to say chi-squared, I'll just say test stat is 9.53, p-value is 0.0015. That's what you'll get on the final. I will give you the StatCrunch shit. You do not need shit. Your job is to do the following. We need to do the 5 steps of the hypothesis test. First thing, we are trying to see if the candies fit the manufacturer's description. If they are a good fit for the manufacturer's description, this is a goodness of fit test. So your job is to tell me what kind of test it is. Then you'll need to give me H naught and HA. H naught for the goodness of fit test is observed values match expected. In this case, I'll say manufacturer's description just to make sure it's clear. Or manufacturer's values. HA is they do not match. At least one. Like with 6 colors, you can have a lot of them be off by like 1 or 2%, and it makes the 6th color be off by like 12%. So like all of them can be really, really close, and then one of them just completely fucking skewed, which looks like what happened with blue here. Well, orange is pretty far off too. That was step 1. So you need to give me the name of the test. 2, you need to give me the null and alternate hypothesis. 3, you need to compare the p-value and alpha. P-value is 0.0015. Alpha was stated to be 0.05. The p-value is less than alpha. I'm expecting to see some shit like this. I strongly, strongly encourage you to tell me what that means. The p-value is too low. Reject the hoe. Support HA. HA is they do not match the manufacturer's description. So that's kind of like a 3B right there. You really, really want to do this because if step 3 and step 4 don't match, I don't know where you got it wrong. I don't know what you didn't understand, but that's like the entire heart of the fucking hypothesis test. Step 4 is our conclusion statement. And here we are supporting HA. There is sufficient evidence to support the claim or show that the candies did not match the manufacturer's distribution, stated distribution. At alpha equals 0.05 level of significance. You get a question like this on the file and you answer like this on the file, 100%. It's really easy to scan a question really quickly and see if the student fucking understood what they're talking about.
Oops.
And part of the reason I don't tell you what stat it is, because like this one is called, it's got a chi-square symbol on it. If you know the name of the symbol, the next test is called the chi-square test for independence. So students see the chi-square on this and immediately think it's the fucking other one and not like read, like they're completely different tests. I don't know why they have like this one's a chi-square test for dependence, or depending on a distribution, I guess, and the other one is independence. But so this one we call the goodness of fit. It's how good or well does the observed values match what we expect. And if you have this, you're flawless. All right, let's go. Everyone got it written down, looks like it. Let's go finish this question here. We said the p-val is too low, we're gonna reject the hoe. We're gonna reject the hoe because there's sufficient evidence that the distribution of colors is not the same as stated by the manufacturer. So notice that their statement of conclusion is almost identical to the way I worded mine. There's a reason for this. All right, that's how we do goodness of fit. Let's take a look at the chi-square test for independence. I like the chi-square test for independence. This is 12.2. This requires tabled data. What we're looking for is whether or not we're checking is if the data in the columns is dependent on the row labels. So you'll see like the population groups across the top. However many there is. And down the rows, you're going to see how they're categorized. Category 1, Category 2, Category 3, however many there is. In fact, this is needed. You need these labels. Labels are needed for StatCrunch. You're going to need a column with the labels in it. And where we find it, since I'm talking about StatCrunch, you're going to go Stats, Tables, Contingency, and then with Summary. These have all the same requirements as the goodness of fit test. All categories have are greater than 1. and no more than 20% are less than 5. Alternatively, at least 80% are greater than or equal to 5. We'll do H naught and HA on the next page, and then we'll do an example. You guys ready? Guys, ladies ready? All right, so H naught and HA. Remember, this is what changes for each of our 5 tests. So H naught for the chi-square test of independence. If you know the name, it kind of tells you or gives you information about H naught. H naught, rows and columns are independent. It's in the name, independence, independent. HA is there is some form of dependence between rows and columns. If you watch the lecture video of this later, some COS students that worked at Cold Stone Creamery did 2 categories, guys and girls, and they did the sizes were like it, love it, gotta have it, the sizes at Cold Stone, and they wanted to know if gender affected cup selection. So the size of the ice cream cup was across the top. The genders were along the rows, and you'll see, I walked through it on the video of whether or not there was a dependence, if being a male or female affected what size cups you have. What do you guys think it was? You guys think it does or not? It does.
A lot or?
It's surprisingly a lot. Guys tended to go for the big ones. The girls always went for the little cups. My suspicion is because girls don't want to look like pigs, even though they really want the fucking big cup, right? You get married, that shit goes away, and you start buying the fucking big cup. Mm-hmm. That's reality. All right, we're gonna take a look at 12.2, number 3. And I'm gonna write the table here. Well, it might be easy for you guys to read because it is big numbers. So let me share the screen. The following data represents health and level of education for 1,626 residents. N equals 1,626. I don't think I need that, but I wrote it. We have education going down the rows. And we have health level apparently going across the top. So we have excellent, good, fair, and poor. And then the first one is not a high school graduate. Number 2 is high school graduate. B is some college like you guys. And D is degree or higher. Degree plus. And for the video, these are the values I got. 51, 56, 69, 60, 147, 142, 145, 107, 126, 81, 87, and 102. Poor is 118, 135, not 135, 134, 105, and 96. All right, so they want to know, does the sample evidence suggest that the level of education and health are independent at alpha equals 0.05 level of significance? I'm going to write that down. Is health and education independent? All right. For the chi-square test of independence, a lot of students want to click on the one that has the equal shit in there, but it's not. Its level of education and health are independent, and HA is the opposite. There is a dependence. Health and education are dependent. It's a dirty trick, because every other problem you do in this, all the hypothesis tests have equal signs. Well, I guess goodness if fit didn't have equal signs. We're going to load the data in. This should load. Can I make this bigger? Yeah, that helps visibility, right? All right, because I want to be able to show you some of the shit you're going to need to see for the boxes. We're going to do stats, tables, contingency with summary. The columns are everything but the column for education. So everywhere health is. Row labels are in education. So you got to tell them what column has the row labels in it, and that does not go in your other columns. So education had the row labels. It's not selected, everything else is. There are some options that we're going to leave the hypothesis test alone. Look at all these different names. There are some options here that are pretty nice to look at. I'm going to show you a couple of them. Expected count is a good one to see first. So like we can see the numbers above. Let's see if I can See the 51, 56, 69, 60. These are the numbers above. This is what we would get if they're completely independent. 100% independent. So like when you're looking at it, you go like, if you're eyeballing, you go, how close is that shit to what it really should be? When we scroll down, it will give us the actual value. We can do the p-value. But like looking at something like this gives me an idea of where it's gonna go wrong. P-value says we're rejecting it because this is a really low p-value. One of these is really far off, if not a lot of them. 134 and 115 is like quite a ways off. Look how close these are, 147 and 147.86. These are pretty, that's not too far off, that's 5. That's 10 away. That's 15 away. That's 15 away. A lot of these are pretty far off. We're gonna write down the I'm gonna write down that test value and I'm gonna write down the p-value. I'm gonna show you some other things in this in case they like ask you questions. I want you to see what kind of cool stuff is in there. So the test stat is 22.740884 and the p-value is 0.0068. So I got what I need from here. I want to show you what some of the other options besides expected count do, because they're kind of neat. And you might find them helpful for things. If we look at row percent, and it resized it like a dirty dog. If you look across the row, for like not a high school student, there was 442 entries. And we had 4 values. Notice 51 is the lowest value and it's only 11.54%. 147 was the highest value and it's got the highest percent, 33. Along the percentages along the rows. So when you do row percent, what you see below each one is the percentage of that thing's value in accordance with the total values of the row. So 51 divided by 442 is 11.54%. 147 is 33.26% of 442. So row percentages go across the row. And then if they want you to look at like columns, you click on column percent, and now it goes across the columns. Going down the columns, notice the percentages are a lot different. But 51, 56, 69, and 60 aren't too far apart. Notice their percentages aren't too far apart either. 69 has the highest. 69 is 29.24% of 236. So that's like a useful thing. I don't know, the old version had you looking at stuff like that. I wanted to point out where you could see them. The options, you can do, it's in the display section. Contributions to chi-square is another one that like really kind of, like wherever the biggest numbers are, that's the one that's fucking it up the most. 1.93, 3.13. That entry right there is the one that's the farthest off, and it's the one that's causing the biggest impact on the results. So you can see like the 147 wasn't doing shit. And remember when the expected value was 147.06, it was like fucking spot on. Doesn't matter what we click for those options to see underneath as the percent or the parentheses, this doesn't change. So if you're not worried about any of that, we're good to go. I am gonna minimize that. We're gonna answer this question. And we'll talk about doing this as a final exam question in a second. P-value to 3 decimal places was 0.007. And p-value is too low. We're going to reject the hoe. So we had a p-value of 0.0068. Well, maybe we should go to the camera real quick and do the rest of the test before we go onward. Okay, so like on the final, that's the kind of shit you will see right there. You will be given the data, you will be given a question. It probably has more words than this, and I know I have a shorter table. This is a big table, it takes up too much space on the paper. You'll be given the alpha. If not, remember the default alpha is 0.05 if they don't give it. Your job is to walk through the tests. Step one, tell me what test this is. Very few questions on this exam have a table. This is like the big one. If it's got a table, there's a good chance it's the chi-square test for independence. Two is give me H naught and HA. H naught is rows and columns are independent. Here, that means health and education are independent. And HA is rows, columns are dependent. With corresponding health and education thing. Step three is compare p-value and alpha. P-value is 0.0068. Alpha was 0.05. As a reminder, go through them one decimal at a time if you're not comfortable rounding. And as soon as the decimal places don't match, compare those. 0, 0 match, the next one is 0 against 5. 0 against 5, 5 is larger, so I'll make the alligator towards the 5. So the p-value is less than alpha, it's too low. We're gonna reject H naught, support HA. And support means there is enough evidence. There is an HA where the rows and columns are dependent. That's what the one we're going to support. There is sufficient evidence to support the claim. That health and education level are dependent. At alpha equals 0.05 level of significance. You get that kind of shit down there? 100% on that question, yeah.
I don't understand what you're talking about, like, if it's independent or independent. How do you know if it's independent?
We're gonna use the p-values to tell us that.
Dependence. 0.5.
So look at let's look at the fair column right here. If the education level doesn't affect it, all of these should be approximately the same value. Does that make sense? Like if it doesn't matter how much schooling you've done, your health is good either way, then we should have the same amount in each column category, but we don't. This is 126, these are in their 80s. The good column, it looks like, well, like, it actually looks like good health. The more schooling you go to, the less healthy you are. The excellent, but in the good column, like those with little education had a higher value than those with like bachelor's or master's. So like, but if it didn't matter, then like it shouldn't matter if I went and like graduated high school or if I have a fucking PhD. There should be about the same number of people that are in the good health range. Does that make sense?
Yeah.
So when you're eyeballing it, you're looking for stuff like that. Does the column stuff kind of like match all down the column? The individual columns don't need to match. It doesn't need to be like 80 across the board. The question is, going down the columns, does that match? And so like eyeballing it is not necessarily as easy as going through and putting it in StatCrunch. StatCrunch, like, it will show you, let me bring that back up. I did contributions to chi-square. Chi-square, it shows which of these categories is saying this is the furthest off. So like this 126 for fair apparently is really far off, and this 81. 126 and 81, if these were all equal, these should be closer to like the 102. But like there's a really high one and there's a really low one in this category. These ones are having a huge impact on the answer. Another way of doing it is if you look at expected count. Expected count will go through and do the math and show you what it should look like. And you can kind of eyeball and go, is it really close? I think the contributions one actually points out which ones do the most damage to it. But if you look at it, 126 to 107, like if this is 126, it should be 107 if it was fair. That's 20 off, which is like 20 out of 126 is like 16%. That's a big difference. It's a really big difference. 20 isn't a lot if this was like 2000, but it's only 120. That's a big number. This is also off by 20. This one's off by 20. 134 to 115, 19. That's off by 19. So like you can see a lot of them are off. But that's the idea. I think looking at the actual values, I like to try to look at it and go, what do I think is going to happen? Like get an idea, like that way I know if the results make sense to me. And here, like these are too far different. Not a high school graduate, like how does graduating high school reduce your chance of having fair health that much? It doesn't say what the dependence is. It doesn't say what's causing what. It doesn't like tell you. Looking at this, if I were to only look at the good health column, to me it looks like if you go to a lot of school, you're less likely to be healthy. Because those with the PhD and the master's degree and bachelor's degree have a lower value. There's less of them. That just might be because fucking grad school and finishing college is stressful. And stress affects health. I don't know. I look over in the excellent health column and there's 60 is a good score. It's the second score out of all of them. So like, if I look at both of them now, what I saw in the good column doesn't match over to the excellent column. So like, it doesn't tell you that like having a higher degree makes you less healthy. It just says there is some sort of connection between these. It doesn't say what it is. Like when you look at the goodness of fit one with the colors, like the M&Ms, we could see which ones were off. Because we wrote down what the expected values were. Blue should have been 98 and it was 62. That's like 50% higher. Over 50% higher. 99 should have gone down to 82. So a lot of these were higher than they should have been, and blue blue should have had the highest percentage, and it was the third lowest score, and it should have been the highest by far. So some of them you can just eyeball and go, nope, blue fucked that up. There's not enough blue candies in that bag. Not so much here. Some of them, it's more obvious. The more rows and more columns you have, the less obvious to see what it is. What one do I have on the fucking practice one? Italian, Chinese, and Mexican food. Male versus female. Question number 10. I can look at this, and just looking at the numbers, I'm going to say that gender affects food choice, because the guys prefer, looking at it, guys prefer Mexican and females prefer Italian. This kind of matches with what I know in my relationship with my wife. She'll want to go out to like pasta, Olive Garden and shit like that, and I'm like, I'll go down on a taco real quick. I love fucking asada tacos and shit like that. We make blackened chicken tacos at home in the air fryer. Fresh crushed avocado, like guacamole, but nothing in it, just avocado. Oh, it's delicious. She likes it too, but she wants pasta a lot more than I do. But some of them are obvious when you look at them, just like that. This one, not so.
So we look at the correlation amongst like the one thing that's being tested and then.
Yes, it's a correlation thing. It's not a causation thing. We're just finding a correlation or a dependence. So the easiest way is to find the fucking p-value, let the machine do the work, and it'll tell you if it matches up. If this is below your alpha level, it's too far out of the expected values for them to be independent. There's a lot of math that you now want to see the formula on. Do I have that with me? Oh, yeah. We went over this in afternoon class yesterday. Just for you guys to take a look. If you want to do even the shit in chapter 11, look at those equations. That's not coming through very clearly. Look at these equations. I don't even know what these fucking symbols are. D bar? D bar is the mean. There's a lot of fucking symbols here. There's S's. S is the standard deviation. S1 and S2 means you got to go through and calculate the standard deviation of each group, which means you need the mean of each group. And then you got to do this formula. This by hand is miserable. Looking at the chi-square test statistic, what we're doing in chapter 12, we did the stuff by hand for figuring that stuff out. But they have a little formula on how they calculate chi-square. It's not pretty. F12 minus F21. What the fuck is F12 and F21? I don't even know what that means. The formulas are not worth it. Trust in the magic. The magic that is the computer. Do you guys want a quick 5-minute break before we do the final section? Let's do that. Let me hit pause. All right, last section, 13.1. Chapter 12 was like proportion for 3 or more samples. Chapter 13 is like on means for 3 or more samples. And we're only doing one of them. 13.1 is the ANOVA test. That's all you got to put on the test is ANOVA. It stands for Analysis of Variance. So the AN is from analysis, the O is from of, and the VA is from variance. Variance is standard deviation squared. So in this one, we test the equality of the mean of 3 or more groups. In StatCrunch, this is stats, ANOVA. It's near the bottom, and then one way. So we, in the following examples, we're assuming that require k different groups, k different populations, with one sample from each. The k populations are independent. What I mean, well, k is a substitute for a number here. So like 3 is the smallest k could be. 3 different populations is the smallest, but we can do 10 different populations. All the populations have to be independent. And they also all need to be normally distributed. You can watch the lecture video on this to see how to check for that if you need to. On the test, you're just going to assume that's the case. And finally, the probabilities have approximately the same variance. This one is one you're going to have to test by hand. Not on the final though. You can assume that it's valid there. The way we check this last one, since variance is sigma squared, we compare sigmas. The sigma for the largest one has to be less than 2 times the sigma of the smallest. And we'll do this in class, you'll see what I'm talking about. I think I cleared the question that's already has it, but if another question pops up, if it mentions SS, it means sum of squares, and it should be in the StatCrunch, and MS is mean of squares, which would also be in the StatCrunch. I think I cleared out the one that has it already. If all that is true, everyone looks ready. What's my H naught and HA? H naught is mu1 equals mu2 equals mu3, which equals up to the kth group. However, there may only be 3 groups, so K would be 3, and we wouldn't have anything past mu3. HA is at least one mean is different. You don't need a bunch of equal signs for this. If there's 4 groups, if there's 10 groups, and the first 9 groups all have the same mean, but the 10th group has a different mean, it fails the test. With that in mind, we are going to do 13.1. We're also doing number 3 in here. And this is on crashing cars. You guys got the H naught HA written down? Okay. It says a highway safety institution conducts experiments in which cars are crashed into a fixed barrier at 40 miles an hour. In the Institute's 40 mile per hour offset test, 40% of the total width of each vehicle strikes a barrier on the driver's side. That's fucked. So like here's the barrier, here's the car, and here's our driver. Like 40% of the car, just off of half, hits the car. Literally the driver's driving into the barrier, the passenger side's missing. This is like, how quickly is the driver gonna live? Because the passenger seat often is empty. A lot of people drive alone, so they really only give a fuck about the driver. Passengers are a fucking, we gotta put seatbelts because some people have families. So 40% of the total width of each vehicle strikes a barrier on the driver's side. Oh, I'm over here talking, drawing a picture. You don't even see what I'm fucking drawing. Marie's over here nodding like, yeah, sure, I see what you're saying. So like, here's the barrier, here's the car, the driver's hitting right into it, and the rest of the fucking car is missing it. The barrier's deformable face is made of aluminum honeycomb, which makes the forces in the test similar to those involved in a frontal offset crash between 2 vehicles of the same weight, each going just less than 40 miles per hour. So it's like 2 drivers driving into each other. You are in the market to buy a family car, and you want to know if the mean head injury resulting from this offset crash is the same for large family cars, passenger vans, and mid-sized utility vehicles. That seems pretty important. How likely are you to get a fucking head injury in a head-on collision at 40 miles per hour? I'm guessing pretty fucking good. 40 miles per hour is not slow, and if you're both doing it, it's a cumulative effect. It's like you hit something going 80. So that's not like trivial. The data in the accompanying table were collected from the Institute's study. So this, like, I don't know how the fucking, they're checking the, I guess they're checking the seatbelt? Because otherwise, in the chair will break. Fucking last car accident I was in, I was going to the Tulare campus, and a diesel in front of me and slows down to turn off road. I brake, slow down just fine. The student behind me is not fucking paying attention. She's on her phone, and she was. Joe just drove fucking right into me, full fucking speed. And I fucking whipped forward, and then I went back, and my chair broke going backwards. Like I ended up looking up like at the roof of my car. It was fucking crazy. I ended up being fine. Like the chair broke rather than me. That sounds like a good thing. But like normally when you would go, impact shoves you forward, especially head on, your body keeps going and the car doesn't. So your head flies forward. Head injury means you're hitting the fucking dash with the steering wheel really hard, which could be breaking your neck. You broke your neck from that? Oh, Jesus. This is all about like how well the seatbelt works, right? So state the null and alternate hypothesis. There's some data. We're going to use that in a second. The null hypothesis is always that the mean is all equal. When you're looking at the mean for more than one or two categories. So all of these say the means are equal for H naught. The one that's different, so HA or H1 is the one we care about. All means are different. That doesn't have to be the case. It only needs one different. So like if the passenger van and midsize utility vehicle are safer than the family car, and it's the only one with a different mean, this test is going to fail. B is the one we want. Normal probability plots indicate the sample data come from normal populations. Are the requirements to use the one-way ANOVA procedure met? Okay, we got to check notice one of these is asking about the sample standard deviation. We got to check the standard deviations for these groups. So I'm going to load this into StatCrunch and we're going to go check them real quick. Now, these might show up in the actual hypothesis test. I don't remember. But we already know how to find standard deviation. We do stats, summary stats, and columns. We'll just do all those three, and I will do standard deviation. And the smallest one is 128. So I'll put this over here. So mid-size car, our mid-size utility vehicle, mid-size SUV basically, had a sigma equals 128. Passenger van. Really? Can we just go with van? What's the difference between a passenger van and a van? More back seats? Yeah, there's back seats. In a regular van, the back is all empty, there's room to store shit. Okay. Passenger van was sigma equals 190, and large family car I got 199 was my standard deviation. So to make sure this works, the largest has to be less than 2 times the smallest. The largest here is 199. Is that less than 2 times 128? 2 times 128 is 256. So yeah, it's less than. So we meet that one. Does that make sense? And we'll check to see if you even need to do stats, summary stats in a second. I don't remember. Let's go back to the question. It says normal probability plots indicate the sample data comes from normal populations. That's what we want. And they should be independent because they're different kinds of cars. So now they want us to find this test statistic, and they give us alpha here. They finally give us alpha. They give us alpha at 0.01. I'm going to draw something on the paper real quick. Something that you will see, like if it's on the final, we'll have the mid, we'll have the van, we'll have the car, and you will see the entries. Data for each listed here. So you'll see a table of numbers, but there's not going to be row headers. There'll just be a table of entries. Kind of like that. You'll see something like that. How this looks different than the chi-square, there's no row labels. That's a good red flag that it's not the chi-square test. There are other ways to list this data, but usually it's like this. So I already have that data in StatCrunch. We are going to come over and do the ANOVA test. It's stats, ANOVA, and one way. We tell it which ones have the data in. It's all three that we have the stuff in. You don't need to click anything else. You can look at other, it allows you to do graphs here if you want. Just look at them. Oh, it does give the standard deviations here. So you don't need to go do stats, summary stats, columns. When you're going through the homework for chapter 13, just do the ANOVA test. And when you need to check to see the smallest or the largest is less than 2 times the smallest, you have the standard deviations here. If the problems ask for sum of square or mean of square, this data is right here. SS is sum of squares, mean of squares is MS. Fstat is our test stat. So I'm going to write down my test stat is 0.412388712, and my p-value is 0.6682. I wonder what these scores are. Like looking at the large family value, the large family cars got like a 400, a 500, 600, but so does a passenger van. Mid-size utility vehicle only has one 500 and everything else is under 400. I don't know. But I do see the p-value, and so that's going to allow us to go on. Fstat was given to us. It was 0.412. Not given to us. We calculated it. And now they're going to ask us to conclude. So let's walk through our hypothesis test real quick. So this is the kind of shit you'll be given. You'll be given the table of numbers. You will be given the test stat. You'll be given the p-value. And some question, it'll like, in this case, are the mean head injuries different? What are these scores from? How much force was on it? How much it deformed? Maybe how much it deformed. I don't know. Either way, we've got a table. That's table. Something will in the problem should indicate mean. You should see something in the problem that indicates mean or average or some shit like that. There should be at least 3 columns, maybe more, but probably 3. So when you see that and it's 3 or more and it's a mean, step 1 is telling me that this is an ANOVA test. Step 2 is H naught and HA. H naught, there's 3 groups here, so mu1 equals mu2 equals mu3. If you feel like saying mu SUV equals mu van, equals mu car. That's more descriptive. I like that, but you don't have to. When I see students go the extra distance though, sometimes I give extra credit on that final exam. Like someone's really trying to fucking make their sums clear. HA doesn't say anything about means, it just says at least one mean is different. It doesn't say which. Then we compare our p-value and alpha. P-value is 0.6682. Alpha was 0.0, I don't even know why they went with 0.01 when fucking p-value is so high. P-value is super fucking high. 66 cents, 67 cents is way more than a penny. This is not too low. Do not reject HA or H naught. Do not support HA. And that means not supporting is not enough evidence. Try to scare the shit out of me up here. There is not enough evidence to support the claim that any of the means are different. For head injuries on SUVs, vans, and cars at alpha equals 0.01 level of significance. You have now seen every hypothesis test, especially if you were here yesterday. And you both were in your own way. The other 20% is two confidence intervals. One's on mean, one's on population. I'm going to give you the lower, like you can see on the question, first question, I give you the lower limit and upper limit. Your job is to tell me that what the confidence interval is. We are 95% confident, and you know, whatever percent confident is, I'll be walking through it at 9:30. You do these, that's all that's needed for this one. If you look on the practice final, the equivalent one here looks like number 3. It says the researcher, when you read through it, eventually says the researcher wanted to compare the difference in means, and there are 3 groups. That's it. That's all I got for today. Any questions?
What if like we happen to fail the mission? Like if
A lot of people got around 50%. After I do the rounding, there's a good chance that probably will go up to 55 or 60 for a lot of people. Either way, like the way it's, if you've been doing all your homework, if you have 100% on your homework, the class is set up that you could literally get a 50 on the midterm and a 50% on the final and still pass the class. So the more homework you do, the better. And getting like around a 50 or so, whatever you got on the midterm, if you did it and didn't get like a fucking 10, you're okay. You still can do well because the final is a lot easier than the midterm. You don't notice there isn't any math here. Like the only math we did is comparing these two numbers. All you need to know is how this hypothesis test works. And it's 5 steps. And the only step that's different for any of them is what is H naught and what is HA. Everything after that is the same. You're looking at the p-value versus alpha. It's still the same, reject or do not reject. Make sure, this is a big thing. We are never talking about rejecting or not rejecting HA. We are either rejecting or not rejecting H naught. We never talk about supporting H naught. H naught has already been supported. That's the old shit. So don't say like that we do not support H naught. We're never supporting H naught. H naught has got its own support. We're checking to see if HA, which is what the new data is about, if that has any relevance to what we're talking about. Is it actually generate anything different than the old news had? Or even if it's not old news, if it's what it was assumed. We may never have done anything on it. But that's what it is. So we're only rejecting or not rejecting H naught. We're only supporting or not supporting HA. And HA is the only one we ever want to talk about in the statement of conclusion, because that's the one we're checking to see if it's true or not. The old one we already assumed to be true. Like the court of law idea, innocent until proven guilty. Innocent is the H naught. We assume that. We're not trying to prove it. The only thing they're ever trying to prove in a court is whether or not you're guilty. And the defendant will try to show that you're not guilty. They can't show that you're innocent. There's no possible way to show that someone's innocent other than, like, if they were a fucking astronaut and got accused of fucking murder and they were on the fucking moon, they clearly didn't fucking do it. They're hands down innocent. At that point, they should say innocent, rather than not guilty. But in almost every single trial, you never know. Someone could have just been a really good mastermind, got rid of all the evidence, didn't get caught on camera, shit like that. They may be guilty as hell. Same idea here. H naught may be wrong, but if we can't show that it's wrong by being able to reject it, we can't just write it off. It still might be true, even if our shit's really different. That's the whole, like, when you get like a p-value of like 0.2, 0.1, you're really like, you're a good chunk away from that value of what the H naught is. Like if the H naught is the mean is like 10 and you have like a mean of 13 or something like that, 10 to 13, that's a 3 difference. When the mean was originally 10, a 3 difference seems pretty big. But it may not be so big that if we took a different sample, we wouldn't get the 10. That's the idea of these hypothesis tests. If I did this again, how many samples am I going to do where that 10 is a reasonable value, or the H naught is a reasonable value? And so we're trying to see if H naught is not a reasonable value, which means like really far out there. All right.
Okay.
Godspeed. I'll see you guys Monday.
Yes.
Oh, we're on Zoom today. Up to you.
Have a good day.
You too. Did you guys grab an extra chest if you want one? They're also on the announcement if you do stuff downloading.